Wideband THz patch antenna with asymmetric Dielectric-Plasmonic Superconductor Waveguide. Abstract: in this paper, a design of end-fire modified wideband THz patch antenna is introduced by employing NBN superconductor working at 8K in asymmetric dielectric-plasmonic waveguide. Compared to conventional design of propst waveguides with metallic particles, utilizing superconductor particles increase antenna's bandwidth up to 12%. Furthermore, far-field radiation of the proposed design is more directive than the conventional one. Keywords: THz patch antenna, superconductor, plasmonic waveguide. Introduction. In recent years, many efforts are investigated to develop terahertz, THz, band communication respect to its high security and wide range coverage 1-8. One of the vital elements in THz wireless technology, which suffer high attenuation path loss, are antennas for broadband, low power transmissions 1-9-10. The microstrip antennas are known the most compact usable components to facilitate multiband and/or broadband, high power and omnidirectional wireless transmission 11. THz plasmonic antennas are nominated by 1-12-13 as an interesting solution for demands of THz wireless technology. However, these types of antennas should have potential to integrate silicon photonics waveguides 2-8. To this end, highly efficient hybrid plasmonic patch antennas are proposed which have the most compatibility with dielectric waveguides compared with other plasmonic designs. Hybrid patch antennas are inspired by multi-layer hybrid plasmonic waveguide discussed in 4, 6, 7 with moderate electric field confinement and propagation losses. In these structures, layers are integrated on silicon-on isolator, SWA, substrates due to their silicon-based nature and have high compatibility with conventional silicon photonic waveguides. In this work, similar to the suggested waveguide in 6, the patch antenna integrated to asymmetric dielectric-plasmonic waveguide is designed for working at neighbor of 1 THz. However, respect to high ohmic losses of metals in THz range, the quality factor, Q factor, of the antenna decreases. To this end, for suppressing metallic loss, metals in the asymmetric dielectric-plasmonic waveguide are replaced with superconductors, which exhibit near zero DC resistance and minimal ohmic losses at defined frequency range. This condition is achievable when superconductors are cooled down below the superconducting transition temperature, Tc, 14. Among different superconductors, some of them such as yttrium barium copper oxide, YBCO, are not suitable for working at THz range regards to showing surface resistance greater than metals, e.g. copper. As discussed in 15, NB can be nominated as the good superconductor candidate because of its low THz ohmic loss. Moreover, experiments revealed NBN superconducting can be work at higher gap frequency compared to NB superconductors and provides structures with lower ohmic loss and higher Q factor as well. In this work, we present the THz patch antenna integrated to asymmetric dielectric-plasmonic waveguide covers 12% wider bandwidth when silver particles are replaced by NBN superconductor. Moreover, higher directivity, 4 dB, is observed in radiation profile of the designed patch antenna in the presence of NBN superconductor instead of silver. 2. Antenna design. In Fig. 1, the schematic of proposed THz patch antenna with asymmetric integrated dielectric-plasmonic waveguide is shown when V-shaped particles are NBN superconductor working at 8K. In 16, both real and imaginary parts of complex conductivity of the NBN film at 8K are derived experimentally for working frequency less than 1 THz. Here, the complex permittivity is calculated from the complex conductivity by employing 1, where is angular frequency, 0.1, 0.2, E0, E8 are real part of the conductivity, imaginary part of the conductivity, the dielectric constant of vacuum and optical dielectric constant, respectively 17. Derived complex permittivity is used in modeling NBN particles in CST simulator. E equals E1 plus IE2 equals E8.2/.E0, plus I.1/.E0, 1. These three particles are deposed inside the silica slot layer, which the majority of transmitted electromagnetic fields are localized there. Also, it is expected by replacing the silver particles with NBN ones, field perturbation in the slot layer decreases dramatically 12-13. Hence, unwanted radiation mostly leaked from the waveguide section reduces, and as a result of this alternation, ultimate gain of the antenna increases. Moreover, this replacement causes the matching between designed waveguide and patch antenna increases, and as a result, bandwidth of the antenna increases. This claim is supported by simulation results provided by CST Microwave Studio registered trademark discussed in Section 3. Similar to 6 and shown in Fig. 1, the mask layer is made from silicon nitride, Si3N4, with 3 times 10 to 3 loss tangent for low propagation loss compared to plasmonic waveguide SU as metal insulator metal, MEM, structures. Finally, similar to 6, to control over layers thickness precisely, metal organic chemical vapor deposition, MOCVD, can be nominated for deposition each layer 18-20. Directivity of the designed antenna is around 0.6 dB more compared to directivity of the antenna with 5M slot layer. It is worth mentioning, increasing thickness of the slot layer, 10M in this case, causes reduction of the electric field confinement in the waveguide section. Fig. 1. Designed modified THz patch antenna with asymmetric dielectric-plasmonic waveguide employed NBN superconductor. 3 simulation results. In this section, simulations are prepared for proposed antenna model to work at 0.8 to 1 THz. As discussed earlier, V-shaped particles are deposed inside the silica slab layer. By making particles from NBN instead, cooled down below Tc, of silver, Ag, it is expected the field perturbation caused by metallic nature of particles suppressed and as result, reflection coefficient, S11, of the proposed design decreases in a wider frequency range compared to the design with Ag particles. In Fig. 2, S11 is shown when V-shaped particles are made from Ag, NBN, and SiO2 respectively. As seen, for Ag particles, the impedance matching, S11-10 dB21, is less compared to 2 other cases and as a result, the bandwidth, f/center, is 10%. On the other hand, for NBN particles the matching increases in bandwidth reaches to 22%, around 2 times more than the one with silver, Ag, particles. This bandwidth improvement will be desired in many applications, specifically imaging application respect to dependency of image resolution to imaging systems bandwidth 22-27. Also, as seen, by choosing SiO2 particles, the field perturbation is perfectly suppressed and S11-10 dB in the whole simulated range. However, the main lobe of the far-field radiation pattern in the designed antenna deviates from θ equals 0 degrees, end fire, when particles are made from SiO2, shown in Fig. 3. Hence, to have directive end fire antenna, NBN particles are chosen. In Fig. 3, far-field radiation pattern at E-plane, phi equals 0 degrees, for the designed antenna at 0.78 THz is depicted for 3 different cases, Ag, NBN, and SiO2 particles. As seen, to have end fire radiation pattern, NBN particles are better choices compared to Ag or SiO2 particles. Moreover, the unwanted radiation leakage for the design with NBN particles is around 7 dB less than the design with SiO2 particles, design with higher bandwidth. In Fig. 4, far-field radiation pattern at H-plane, phi equals 90 degrees, for the designed antenna at 0.78 THz is depicted for 3 different cases, Ag, NBN, and SiO2 particles. Similar to E-plane simulated results, the main lobe is close to θ equals 0 degrees, when V-shaped particles are made from NBN superconductor. Next, the far-field radiation pattern at H-plane, phi equals 90 degrees, for the designed antenna at 0.98 THz is illustrated in Fig. 5 for 2 cases, Ag and NBN particles. At this frequency, center frequency of designed antenna with Ag particles, still the end fire main lobe of the radiation pattern is higher, around 4 dB, when NBN superconductor particles are considered for the design. Finally, the far-field radiation pattern at E-plane is depicted in Fig. 6 at lower edge of the frequency band, 0.75 THz, of the designed antenna with NBN particles for different silica slot layers thickness. As seen, for 10M thickness, the Fig. 6. Far-field radiation pattern at E-plane in lower edge of the frequency band, 0.75 THz, of the designed antenna with NBN particles for different silica slot layers thickness. For conclusion, in this work, modified THz patch antenna is proposed, which is fed by asymmetric dielectric-plasmonic waveguide. Unlike conventional design discussed in 6, in the new design, NBN is utilized for directive V-shaped particles and is cooled down to work as the superconductor. As a result, the bandwidth of the antenna is around 12% more than the bandwidth of the case with silver particles. This bandwidth improvement is justified based on improving matching when superconductor is employed in waveguides used for exciting antennas.